This first part of Chapter 8 is a review of statics. We will be solving for the reaction forces and reaction moments of beams with point loads, uniform distributed loads, and non-uniform distributed loads. 6 chapters in the book focus on beam problems, so it's important to be able to find the reactions quickly and accurately. We'll start with a single point load on a simply supported beam. We have 2 equations. The sum of the moments about any point is 0, and the sum of the forces in the y direction is 0. In the next few chapters, we won't be solving any beam problems with forces in the x direction. We have 2 unknowns, r sub a and r sub b. So the number of equations matches the number of unknowns. First, we'll start with the sum of the moments. In most strength of materials textbooks, the counterclockwise direction is defined as the positive direction for moment. Therefore, the moment created by the 5 kip point load is negative about point A, and the moment created by r sub b is positive about point A. Solve the equation for r sub b, and the answer is 1.67 kips. We can find r sub a in either of 2 ways. We can either solve the sum of the moments about point B, or we can use the sum of the forces. I think sum of the forces is simpler, which means it's less likely that I will make a mistake. Most strength of materials textbooks define up as the positive direction. The result is 3.33 kips. After solving for the reaction forces, it's a good idea to check if the answers actually make sense. Since the point load is closer to the left end of the beam, it makes sense that r sub a is bigger than r sub b. What if we have more than one point load? The sum of the moments and the sum of the forces equations each have one more term for the added point load. If a single point load is at the midspan of a simply supported beam, then the reaction forces are the same. The beam is symmetrical, and each support carries half of the applied load. When you have problems that look like this, you don't need to work out the sum of the moments and the sum of the forces in your homework. Simply state that, by inspection, both reaction forces equal 1/2 of the applied load. What if the load is a uniform distributed load instead of a point load? We start by drawing an equivalent load diagram, which replaces the distributed load with a point load that acts at the centroid of the distributed load. In this problem, we have a uniform distributed load in the shape of a rectangle. So the centroid of that rectangle is 1 meter from the left end of the beam. The equivalent load is 3 kilonewtons per meter times the 2 meters it acts on, equaling 6 kilonewtons. Now you can solve for the reactions the same way as in the previous problems. What if the load is a non-uniform distributed load? We use the same method, but the area under the distributed load is the area of a triangle, half of the base times the height. You can find the centroid of a triangle in Appendix C. It's 1/3 of the distance from the thicker end of the triangle and 2/3 of the distance from the pointy end. Otherwise, you solve the problem the same way as before. If the supports are inboard of the ends of the beam, we call it an overhanging beam. This is how cars are made. The wheels aren't out at the bumpers. Instead, the car sticks out at the front and the back, beyond the wheels. Since there's a distributed load, the first thing we have to do is draw an equivalent load diagram off to the side. The equivalent point load is 200 pounds. I like to redraw the dimension lines so that they all reference point A. Now it's easier to plug in the right lengths into the sum of the moments calculation. Notice that the first term is positive because a 100-pound load creates a positive moment about point A. It wants to rotate counterclockwise, which we call positive. When we solve for r sub b, this term becomes negative. If you miss that in your solution, you will get the wrong answer. The easiest type of beam to solve is the cantilever beam, because you can start with sum of the forces. All the forces pushing upwards must equal all the forces pushing downwards. So the reaction force at the wall is 5 kilonewtons. The sum of the moments at the wall is also 0, but that doesn't mean that m sub b is 0. The sum of the moments at the wall is m sub b plus the moments created by the applied loads. We're still using the convention that counterclockwise is positive, so m sub b is marked as a counterclockwise moment. When we do the math, we find that the result is a negative number. This means that the actual moment at the wall goes the other way. It's actually clockwise. There are several fully worked out examples in the book that show you how to calculate beam reactions.